All right, so we're never done with compound interest, and so here we are revisiting it. So if we let P be the initial amount of money that we deposit into some account, then we let A be the amount in the account at any time T in the future. Instead of assuming the money in the account earns a particular rate of interest, suppose we say that the rate of growth of the money in the account at any time T is proportional to the amount present at that time. So since dA dt is the rate of growth of A with respect to time, so it's a change of A with respect to time, we've got dA dt is equal to RA. And A of 0 is going to be P because at time 0, that's what we're plugging in, that principal amount. And A and P both have to be greater than 0. So that's kind of a key piece here. Now, R is going to be an appropriate constant, so it's some rate. Now, we'd like to find a function A equals A of t that satisfies these conditions here, okay? So what we're going to do is we're going to multiply both sides of this equation by 1 over A or divide by A, however you want to look at it. And when we do that, we get 1 over A dA dt is equal to R, okay? Now what we're going to do is we're going to integrate each side with respect to time. And so now we've got the 1 over A dA dt equals that R dt. Okay. Well, dA dt times dt, guess what? Those dt's cancel, or we can take it to the other side is really what we're going to do. And so then we really just have this is equal to this, so they've canceled. And so now we take the antiderivative of this, which we know is ln of absolute value of A, and an integral of this is going to be R times T because it's in terms of T here, and then plus C. And now, since this is absolute value of A, it has to really actually just be equal to A in this case because we said over here, A and P both have to be greater than 0. So because of that, we don't have to worry about that absolute value because it's always going to be positive. And so now we have this. Now, what can we do with that? Well, now we can solve this and get A. Well, how do we get at? Well, we have to take E to both sides. And so when we do that, E to the ln of A is going to be A. And then we have E to the RT plus C on the right side. Okay, so that's what we end up with here. Now we have to know some properties of logs. If they have b to the m times b to the n, that's equal to the b to the m plus m, n plus n, however you want to look at it. And so what we can do is we can split that into a equals e to the c, e to the rt. Okay. Now the key here is, remember, at time 0, we have principal p. Okay. So what we're going to do is we're going to evaluate this at time equal to 0, and then we're going to set that equal to p. So this is going to be p, and we're going to set the t equal to 0. Well, that becomes e to the 0, so that's just 1, and that's still e to the c, and that's equal to p. And so basically we have e to the c is equal to what? P. And so now, since that's equal, what we can do is say, well, that becomes a equals p e to the rt. And that's the famous equation we know, a equals PERT, and that's the continuously compounding interest formula obtained way back in 11.1, where the principal is invested at an annual nominal rate R compounded continuously for T years. Okay, so that's something we've done, we've looked at, and so we know how to do that. All right, so let's pause there and we'll come back with some more exponential growth law.